Good day, grade 10s. How are you guys doing today? Welcome to this chemistry lesson number 18. Today we're going to be looking at percentage yield, and then in the next lesson we'll look at percentage purity. It's also in continuity to stoichiometric reactions. So by the end of this lesson, we should be able to define what percentage yield means, recall the formula for calculating percentage yield, which is given in the document, and calculate percentage yield if given a set of scenarios, given what's called an equation to say a certain amount of reactant, maybe say reactant A reacted with reactant B, and this was produced, and you can then tell to say what is the percentage yield. Okay, so basically what we'll be doing in this lesson and what this concept is about is to show that sometimes even though you have certain quantities of reactants taking part in a reaction, some of the material is lost. Some of the material is lost. It's not destroyed, but it's lost. And as such, you must be able then to calculate to say, we would have expected to get this much, but because of factors beyond our control, we got less. So that's the percentage yield. But you don't get more, right? You get usually you get less. Okay, so just look at the objectives and get yourself ready for this lesson. So just pause and try and look at what the word yield means. Look at what the word yield means. Okay, percentage yield. Okay, so we are given the definition of the term percentage yield as referring to a way of determining the amount of products formed during a particular reaction. Percentage yield is calculated by using the following formula. But what I want you to understand is to say, if you are saying you have two reactants, maybe one reactant has a mass of 50 grams and the second reactant, let's say reactant A has a mass of 50 grams and reactant B has a mass of 40 grams. If you add them together, you would expect your resultant product AB to have a mass of 90 grams. But you will find that sometimes the product AB can have a mass of 89 grams or 88 grams. So you would then want to calculate to say, if we were expecting 100 grams or we were expecting 90 grams, but then in the end we ended up getting 88 grams, what then is the percentage yield? Okay, to say you were expecting, let's say even in the exams, when you write an exam, you expect to say, okay, if I get everything correct, I'll get 100%. Whether it's out of 50, whether it's out of 30. In percentage, if you get that out of 30, that's 100%. If you get 25 out of 25, that's 100%. But what happens when you get 19 out of 20? That's no longer 100%. So you now, what calculated, you effectively just change it to a percentage. And you change something to a percentage by saying the actual number that you got over the expected number. Right? So if you're expecting to get 10 out of 10, but then you get 9 out of 10, it means you say 9 divided by 10 multiplied by 100%. That changes it to a percentage. And in this case, it's a percentage yield because we have substances reacting. What we'll do quickly is I will play a video which explains this concept also, so that I think it's also clearly described there. So let's just watch that one.
As you will have seen in our videos on molecular masses and conservation of mass, it is possible to predict the theoretical mass of products formed in a reaction. For example, take the reaction of ethene and water to produce ethanol. Ethene has a molecular mass of 28, water a molecular mass of 18, and ethanol a molecular mass of 46. From this, we can deduce that using 28 grams of ethene and excess water, the theoretical mass of ethanol formed is 46 grams. However, this grams of water.
Right.
For example,
So let's
take the reaction of ethene
right
and water to produce ethanol.
here. Don't worry about. Of course, very soon, even now, you now have to know what ethene is. You now have to know what ethanol is. Okay, this is a hydrocarbon. This is an alcohol. Okay, but what we are mostly concerned with here is the masses. To say the reacting mass of ethene plus the reacting mass of water. If you add them, they give you the molecular mass of 46. Okay, so if you add the different masses, the masses of your two reactants must be equivalent to the mass of your product. They must be equal to the mass of your product. When we are doing it on chemical equations on a paper, theoretically, but in reality, it's not like that. In reality, you have loss, right? You have loss. So instead of 46 grams, you get something less. Okay?
6. From this, we can deduce that using 28 grams of ethene and excess water, the theoretical mass of ethanol formed is 46 grams. However, this is very much a theoretical mass. In practice, the mass of the product formed is actually less than the mass we predict due to the inefficiency of the reaction process.
I hope we know what the word efficiency means. Efficiency and inefficiency. Okay? We talked about efficiency in machines. Efficiency in machines where you find that if you put in 100% or if you put in 100 newtons of work and then you get out 100 newton output, then you know that you have a highly efficient machine. But we know that inefficiency means that some materials or some energy is lost during a reaction.
This can be for a variety of reasons. Not all the reactants being used up, products escaping the reaction vessel, or even the physical loss of products during transfers.
Okay, so if we are looking at reasons why, because you have to be able to explain, to say, I got less products than my reactants. Why? Why did I get less products than my reactants? And then you know that, okay, maybe some of the reactants didn't actually take part in the reaction. Because when you write an equation and we just say ethene plus water, we assume that all the ethene is going to react. But some of it might not react. Okay? Some of it might not react, maybe due to the temperature or to the pressure of the reaction vessel. Yes? So that results now in less of the ethanol being produced. I'm just giving that one also as an example. But try to think of the reactions that you know. Try to think of the reactions that you know. Okay? I think what you should do now is just pause the video and write the equation for the formation of methane. Right? Write the equation for the formation of methane, where you have carbon reacting with hydrogen to form methane. So please just pause that video and write the masses, the reacting masses, and of the reactants, the masses of the reactants, and the mass of your product. Okay? And try to see what would happen if there is a less product. The mass of the product is less than that of your reactant. Okay, so another reason why the product the mass of the product might be less, okay, it might be less, is because when you weigh, let's say you have taken your sodium hydroxide, you have weighed it, you want to react it with maybe some sulfuric acid, okay, then what happens is that you may actually spill, not a lot, but you might actually just spill a few drops of that sodium hydroxide. So theoretically you would have said, I'm using this particular mass of sodium hydroxide or this particular volume of sulfuric acid, but then you spill some of it over. That means you have actually lost some of the products, some of the reactants during the reaction itself, or if you have these reactions where the materials are almost explosive, some of them will actually be boiling and spilling out of the reaction vessel. That causes also your final product, the mass of the final product, to be less than what you would have expected. Okay?
Percentage yield tells us the efficiency of a reaction in that it shows us the amount of product that was practically made as a percentage of the mass of theoretical product that should have been made. To calculate percentage yield, we therefore do the actual yield of product formed divided by the theoretical yield of product formed multiplied by 100.
Okay, so actual yield, right? When you say what is your yield, you say what have you produced, right? Actual products, effectively, or actual quantity of products formed, right? So yield can also just be, let's say, synonymous with quantity. Okay, actual quantity of products formed over theoretical quantity of products formed. Say you expecting this, but this is the actual. So you have the actual over the theoretical multiplied by 100 because this is percentage yield.
Let us now look back at our example, in which we had calculated that 28 grams of ethene produced a theoretical yield of 46 grams of ethanol. Let's say this was carried out in practice, and only 42 grams of ethanol was actually produced. We therefore need to work out 42 as a percentage of 46. This will
now observe. So if you're told that okay, the expected yield is 46 grams, but then actually you have found 42 grams. That means that from that position alone, it's extremely simple for you to calculate the percentage yield. Yes? Because now all you're going to say is 42 divided by 46. To say, I was expecting to get 46 grams, but instead I got 42 grams.
show us the percentage yield. Using the calculation, we do practical yield, 42, divided by theoretical yield, 46, which equals 0.913, multiplied by 100, 91.3%. It can now be clearly seen that in this reaction we only produce 91.3% of what was expected. In industry, to ensure we have maximum reaction efficiency, we would now modify our methods to improve this yield.
Okay, so given that these things need to have actual applications in real life, okay, you then, if you're then working for a company and then you find that your actual yields are maybe 60%, 50%, 65%, it means that you are losing a lot of your reactants. So as a chemist, you must be able then to observe the reaction and say, okay, we think that we are losing a lot of our reactants because of certain conditions. Our vessels, the apparatus that we're using, are they proper in terms of, are they not damaged, are there no leaks in terms of the temperatures that you are using to carry out particular reactions? Are you using the best physical and chemical conditions for the particular reaction that you'll be observing, right, or monitoring as a chemist? So what we'll then move on to is the actual calculations. So what we have there is an illustration. It's already calculated. So what I want you guys to do is to follow the steps. Try and follow the steps. We have been doing this for a couple of weeks now, and by now I'm sure you know that there is no way that you just read these things and go by. You have to write it down in your own book. You have to write it down on a paper. You have to follow it stage by stage. You have to follow it stage by stage. What we'll do is I will do this particular example with you guys in today's lesson, and I will probably give you another one if we were able to finish all these parts, because now we've been struggling to finish, you see, all the parts. But then just go through this one, try to make heads and tails of it so that you are well equipped when I start asking you what is meant by these respective calculations. But the theory, the foundation is what we have discussed, and that is what is very important. What's very important is to know why you're doing something. Know why you're doing something. Don't just punch numbers into your calculator. You just see a 3 and a 5 and you just punch. Punch for what? Right? Understand why you're doing something. Understand why you're doing something, and you will find that the answers will most likely be much more simpler to attain. So thank you very much, guys, for watching this video. See you very soon in the lesson.